Now that we've done our principal component analysis, we're ready to explore the data using those principal components. So what we're going to do is we're going to concentrate on one particular type of measurements, which is the snow depth in New York State, because it is a particularly nice set of sequences where you can see the effects of the different eigenvectors very clearly. So as we saw before, the average of snow depth is something that is maximized around February, March, and of course is 0 during the summer, and again increases after October, November. So that's the mean, and the standard deviation shows us that, of course, there is much more fluctuation when there is snow than when there isn't snow. When there isn't snow, the fluctuation is 0. Okay, so we have to read some information in before we do this analysis. So the first is we're going to read the statistics file, the pickle file that has the statistics for the state of New York. And here is what we did, and it shows us that we got the statistics for these 6 measurements. We are only going to use snow depth. Next, we're going to look at computing the decomposition of each row, each particular year of snow depth. We're going to then add these coefficients that give us the description. So to remind you, if the original vector here is v, then the first approximation is simply using the mean. So that's the residual after we approximate using the mean. The second approximation, or R1, is the approximation where we take R0 and we subtract the first component, the first principal component. Okay, so that gives us the second one, and then we continue in this way. R2 is R1 minus the second eigenvectors, and R3 is the next one, and so on. So for each residual, we compute its square norm, this is what we call the residual norm. Okay, so we basically take the residual vector, and we just take the sum of the squares of the components. And that is essentially our measure of how good our approximation is. So this is a central thing in many things that we will do from this point on, where the quality of our approximation is measured by what is called the root mean square, or the root of this quantity. Okay, so the smaller the norm, the better the approximation. So a few things that we know from linear algebra. First of all, the 0th residual is the square distance of the vector v from the mean mu. The kth residual is the minimum square distance between the vector v and a point that can be expressed in the following way: mu plus some coefficients times the eigenvectors for the first k eigenvectors. So you can think about it as the first approximation I have is a point, the second approximation I have is a line, so I just choose the best point along that line. The second one is that I have a plane, and I choose the closest point to v on that plane, and so on. So the residual norms are non-increasing, so we're necessarily getting better and better as we're adding coefficients. And moreover, once we get to using all of the principal component, that is basically a complete orthonormal basis, and we recover the exact vector initially, the exact initial vector. Okay, so basically any vector can be represented in this way, but the question is, how well is it represented using just the first k eigenvectors? Okay, so the function decompose data frame extract a series from a particular row, computes the k decomposition coefficients and the square norm of the residuals and constructs a new row that resembles, that is reassembled into the new, a new data frame. Okay, so what we are doing is basically we're taking a particular row that represents a particular year of snow depth, and then we're representing this year using the top k coefficients. And then the next thing that we'll do is we'll plot that. Okay, so here is one such thing. And this is done for each row. Okay. So now that we have that information for each year station, we actually would like to have also some additional information about the station that might relate to how the snow depth in that place behaves. Okay, so we're simply going to do a join of the information that we generated, the breaking up each vector to the first k components, and then we're going to use that in our plots. Okay. Here's one subtlety to make the analysis better. What I saw after playing around with the data is that while the first approximation, in general, the best approximation that is a single vector is the mean, because there are places where they don't get any snow, a much better approximation for those is simply the zero vector, so no snow accumulation ever. Because those vectors are so different, because basically there's very little to say about snow accumulation when there is no snow accumulation, I choose to remove all of these sequences, all of the year stations, such that there is almost no snow. So more specifically, I filter out vectors for which the mean is a worse approximation than the zero vector. So if the zero vector explains the data better than the mean depth of the snow, then we're basically saying, okay, these are places that have very little snow. Let's not put them into our analysis. Okay, so now let's just refresh what we did before and plot the mean and top eigenvectors. So if you remember, this vector right here is the mean. Okay, so basically it shows you what is the snow depth on average, and then here we have the eigenvectors. Okay, so we have the first eigenvector is the blue, the second one is the orange, and the third one is the green. And then we want to see that really these vectors can explain a lot of the way that the real sequences are. And so this is this plot. So this is the kind of plot that you really want to see, whatever you're generating a model, be it from eigenvectors or from something else. And what it says is that if you just use the first eigenvector, you reduce 60% of the remaining variance after subtracting the mean. And then with the second one, you get to almost 70, and with the first four, you get to 80. So four of the eigenvectors explain 80% of the variance. If it was completely random, what you would get is 4 divided by 365. So it would be way down here. So this is good. This basically tells us we have a model that is a good representation, or to say differently, if you take a 4-dimensional hyperspace around the mean, then it can approximate very well what sequences you get. Okay, so now what we want to do is explore the decomposition. So first, let's start with intuitive analysis. So we have here the the vectors, the eigenvectors, and the mean. Okay, so the mean is the blue line, and we are going to basically just look at what this looks like. So the first eigenvector looks very much like the mean. So what does that mean? It means that if I add the first eigenvector to the mean, I increase the mean, and if I subtract it, I decrease the mean. Okay, so that basically is like multiplying the mean by a constant, and above 1 or below 1. And that basically means that this eigenvector just represents how much snow on average does this place get. Okay, below the general average or above the general average. But the shape remains the same. Eigenvector 2 is much more interesting. It basically is positive in the first part of the winter here, and it is negative in the latter part. So what does that mean? It means that if you add this vector, the green vector, to the mean, it basically shifts the mean, shifts the peak to early on in the winter. And if you subtract it, it shifts it to later on in the winter. So this is basically representing whether snow is late or early. And finally, the third eigenvector is positive in February, and it's negative in January and March. So what does that mean? It means that if you have a positive coefficient on this eigenvector, that makes the snow season short, right? It basically, it peaks it around its maximum, and it reduces the amount of snow before and after. And vice versa. If you take negative, then it makes the snow season longer. Okay, so this is a first cut. This is just intuition. We want to back this up with some more analysis and visualization, and that is what we're going to do in the next video. See you then.